and welcome back. We'll continue looking at section 2.7 on inverses. So let's just go through a couple of examples where we find inverses of functions. We're given a function f of x is 4x cubed plus 1, so we want to find the inverse. In the first order of business, we will replace f of x with y. And the inverse should swap the input with the output. It should undo the original function. Well, if the input was x and the output was y, when we swap them, we'll just swap our x's and y's. And now we will solve for y to find the output of my new function. So I will subtract 1 from both sides. I'll divide both sides by 4. And now I have y to the third power. So what I will do is I'll raise both sides to the 1/3 power. And y to the third power to the 1/3 power, we multiply powers, and this is just going to end up being y. And this other side is just going to be x minus 1 divided by 4 to the 1/3 power. We can rewrite this. This can also be rewritten using cube roots. So this is going to be x minus 1 over 4, and it's going to be the cube root of all this. These two things mean the exact same. There's no difference between them. It's whichever one you like. I tend to think of things in terms of the powers anyway. So this is the inverse of this function, and one good thing to do would be to check really quick whether or not these are inverses of one another. So this function, when I call this y, what I mean now is this is going to be my new inverse function. So let's plug this into our f of x. So f of f inverse of x, f inverse, I'll just use the root here. Oops. So we take this times 4, and we raise it to the third power, and we add 1. Well, we have a cube root that we're raising to the third power, so those will cancel out, and we'll get 4 times x minus 1 over 4 plus 1. Again, the third root and the third power will cancel out. We can think of it as to the 1/3 power raised to the third. And then times 4 divided by 4 will give us x minus 1 plus 1, which gives us x. Now, technically, we should also do the other way. We should plug f of x into the inverse function, but I've run out of space here, so I'll just stop here. We see that we do get an x. So we should check to make sure that f inverse of f of x is also equal to x. Let's look at another function. So let's find the inverse of x plus 1 divided by x minus 5. Again, we start in the same way. We let y equal the output to the function. Then we switch inputs and outputs. So we're going to have x is equal to y plus 1 over y minus 5. Now, note that up here, x can't be equal to 5. We can't plug a 5 into this function. So anywhere we go, we're not allowed to plug in x is equal to 5. So when we solve this, I've got a fraction on this side. I want to get rid of this fraction. So what I will do is I will multiply both sides by the denominator. So I'll just multiply both sides by the denominator. And my reason for this is the denominators will cancel out. And what I'm left with is going to be a y minus 5 times x. And that's going to be equal to a y plus 1. Now, a few more steps. Let's distribute the x here. So we'll have y times x minus 5 times x is equal to y plus 1. And the goal is to solve for the output, which is y. So I'll get all my y's on one side, and I'll get everything else on the other. So I will subtract a y from both sides, and I will add a 5x to both sides. So the 5x's will cancel out, and the y's will cancel out, and I'll be left with y times x minus y is equal to 1 plus 5x. And I want to get y by itself, so I can pull a y out of both of these terms. If I pull a y out of this first term, I'm left with an x. If I pull a y out of the second term, I'm left with a 1. So nothing happens to the other side, and now I can divide both sides by x minus 1. However, I can only divide both sides by x minus 1 when x is not 1. So let's remember that for the end. And after I do this, on the left-hand side I'll have y. I'm just going to reverse this order just so that's a little bit clearer. I'm going to write 5x plus 1 instead of 1 plus 5x. It doesn't make a difference. And on the bottom we'll have x minus 1. So the inverse function here, f inverse of x, should be 5x plus 1 divided by x minus 1. And again, we're not allowed to have x minus 1 be plugged into our inverse function. This is one of the functions where, when you look at this versus the original function, x plus 1 over x minus 5, this inverse is not as obvious to me. However, to plug it in and check that it is the inverse would take a little bit long, so I'm going to skip that step for now. It's something that I would encourage you try plugging these functions into one another and making sure that they are inverses of one another. So let's do one more quick example. Let's find the inverse of x squared. So again, we'll replace f of x with y, and then we'll switch our inputs and outputs. So we'll have x is equal to y squared. I'm going to reverse the order of this just so that it's a little bit clearer. I haven't done anything. And now, when I want to solve for y, y could be equal to x, the square root of x, or y could be equal to the negative square root of x. And here we have a problem. If I want to define a function, whenever I'm given an input to the function, I have to tell you what the output is. Well, do we choose the positive square root, or do we choose the negative square root? In this instance, this right here means there is no inverse. Any time that you have to make a choice, which one do you want for your output? If there are multiple things, there cannot be an inverse. Another way to see this is if we were to think about f of x. If I plug in negative 2, negative 2 squared should be 4. And if I plug in 2, 2 squared is also 4. So when I'm thinking about what should the inverse be, well, the inverse of 4 should be whatever we plugged in to get 4. Well, which do we choose? Do we choose a negative 2? Or do we choose a 2? And it turns out that this means this function can't exist. So there is a quick way to see whether or not a function will have an inverse, and it is called the horizontal line test. And it's very, very simple. You draw a horizontal line through the graph. If it intersects it more than one point, no inverse. If it has an inverse, then the horizontal line will only ever intersect it at one point. So here, for instance, is the graph of x squared, and we can see that if we draw a horizontal line through it, there are 2 places it intersects. So no inverse. exclamation point. Here is a graph of a straight line. If you draw horizontal lines through it, they only ever intersect in one place. That means it has an inverse. Has an inverse. So this is just a very quick way to see if something has an inverse. Here's a function that we haven't seen yet, but we will later in the year. This is the function f of x is equal to e to the x power. We haven't defined what e is. It's just a number, and we're raising it to the x power, whatever that means. And we can see that just from the graph, if you ever draw a horizontal line, it will only intersect the graph at one place. Whereas over here, if we look at x cubed minus x squared, up here, this only intersects the graph at one point, but I can find another horizontal line that intersects it at 3 places. So if you can ever draw a horizontal line that intersects it at more than one place, there is no inverse. Whereas over here, we only ever get one intersection, so this means that this function has an inverse. The last thing that we'll do in this video is look at the graphs of f and f inverse. So when we think about the difference between f and f inverse, what we've done is we've swapped inputs and outputs. Whatever you plug into f and then get out, if you plug that into f inverse, you'll get what you started with. So we're switching our x's and our y's. Well, if we're swapping x's and y's, that should be pretty easy to graph. And it turns out that it's just a reflection. So what we'll do is we'll take this graph. So we have this function. It starts here and then sort of comes up. What we'll do is we'll draw this line where y is equal to x. So this is roughly this line. And if we reflect everything across this line, it will look a little bit like this. So this would be the graph of f inverse. Also, just as an aside, this function does have an inverse because if I ever draw a horizontal line through it, it only intersects it once. So we just swap our x and y coordinates, and we've got the graph of f inverse. So this makes it kind of nice. So the graph, so in this example, the graph of a function has two line segments, one from -2, -2 to -1, 0, and then we carry on from -1, 0 to 1, 2. So let's graph f and its inverse. So the graph of f is pretty straightforward. There's a line segment from -2, -2 to -1, 0. So here is, maybe I should make this white. Here is -2, -2, and here is -1, 0. So there is just a line segment going straight up. Shouldn't say straight up, going from one point to the other. And then going from -1, 0 to 1, 2. So 1, 2. So there is the second point. So we've got 2 line segments. And now we want to graph its inverse. Well, what we can do is we can take these line segments and we switch the x and y's, just like when we're finding the inverse if we have a formula. So for the inverse, we're going from -2, -2. If I swap these around, it's still in the same order. So -2, -2. And this goes to 0, -1. No, I've just swapped x and y. And then from this one, it's going from 0, -1 to 2, 1. Oh, and that's pretty easy. So we're going from -2, -2, so it's still this point, going to 0, -1. And then we're going out to 2, 1. 2, 1. So here was f, here is f inverse, and we can see that it's just a reflection about this line. If I could draw better, it would be a little bit more accurate.